Let's write down the metric describing the geometry outside an isolated spherical non-rotating body of mass m. All right, written as a line element, it's ds squared equals minus 1 minus 2m over r dt squared plus 1 minus 2m over r inverse dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Now, like any metric, it can be written in lots of different coordinates. The particular coordinates that I've used here are called Schwarzschild coordinates. So these are the coordinates t, r, theta, and phi. And the geometry described by this line element is often referred to as the Schwarzschild geometry. Or we might also use the term Schwarzschild spacetime. And we might use these terms even if the line element or the metric is written in different coordinates other than Schwarzschild coordinates. So how do we know that this metric describes the geometry outside an isolated spherical non-rotating body? Well, one way to convince ourselves would be to solve Einstein's equations. So this metric is a solution of Einstein's equations. Now, we haven't talked about Einstein's equations yet, but Einstein's equations relate the space-time curvature or space-time geometry to the matter distribution in space-time. And if we solve those equations for an isolated spherical non-rotating body, this is what we find. Of course, you might ask, how do we know that Einstein's equations are correct? And the answer is that, well, they've been verified to a high degree of accuracy by lots of different experiments. So for now, let's just take this metric, this geometry, as a given that has been verified by experiment. What are some examples of isolated spherical non-rotating bodies? Well, how about the Earth? All right, the Earth isn't entirely isolated. There's the moon nearby, and there's the sun and Jupiter and so forth. But the moon is pretty small, and the sun is pretty far away. So to some degree of approximation, the Earth can be considered as isolated. The Earth also isn't exactly spherical. It bulges at the equator and has mountains and valleys. But again, to some degree of approximation, we can think of the Earth as spherical. We can also think of the Earth as non-rotating, compared to, say, a pulsar, which is a rapidly rotating neutron star. The Earth rotates pretty slowly. So the Earth is a pretty good example of an isolated spherical non-rotating body. And likewise, to some degree of approximation, we can think of the Sun and Jupiter and so forth as being isolated, spherical, and non-rotating. Keep in mind that the Schwarzschild geometry is the geometry outside an isolated spherical non-rotating body. So here's my body, the Earth or the Sun. The Schwarzschild line element Schwarzschild ds squared. Let me just say the Schwarzschild metric applies out here. Right, not in here. So in here, inside the body, ds squared, the metric is something else. And we can, in principle, we can find out what it is by solving the Einstein equations. And the answer will depend on the details of how the matter is distributed inside, and it can also depend on the stresses inside and so forth. But remarkably, the geometry out here doesn't depend on any of those details. It only depends on the total mass. Let's take another look at the Schwarzschild metric, and let me make a comment about units. In writing the metric this way, I've assumed that the speed of light and Newton's constant are both equal to 1. So the units have been chosen so that c and big G are both equal to 1. So if we are working in units in which that's not the case, so the speed of light and Newton's constant are not equal to 1, the Schwarzschild metric is minus c squared 1 minus 2gm over c squared r dt squared plus 1 minus 2gm over c squared r inverse dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So I'm assuming here that ds has units of length. I'm assuming that the coordinate t has units of time, the coordinate r has units of length. Theta and phi are both angles, so they're dimensionless. And if we look at this factor, I'll remind you that the dimensions of c are, of course, length over time. The dimensions of big G are length cubed over mass times time squared. So if you put that all together, you'll see that this term is dimensionless. Now let's return to the usual practice of setting c and g equal to 1. So the Schwarzschild metric is minus 1 minus 2m over r dt squared plus 1 minus 2m over r, the same factor, but this time inverse, dr squared plus, and let me write the remaining factors with r squared factored out. So this is r squared times d theta squared plus sine squared theta d phi squared. What can we tell about the Schwarzschild geometry by examining this metric? Well, one thing that we notice is that the metric components, g mu nu, are independent of the coordinate phi. And this tells us that the vector field d by d phi is a Killing vector field. So in other words, the geometry has a symmetry a rotational symmetry. In fact, you'll notice that this portion of the metric is the same as the metric on a two-dimensional sphere of radius 1. And the two-dimensional sphere is symmetric not only about rotations about the z-axis, that would be rotations along d by d phi, it's also symmetric under rotations about any axis. So we refer to that as spherical symmetry. So here's the sphere. Here are the coordinate lines d by d phi, but the sphere is also symmetric under rotations about any axis. So these are the integral curves of some Killing vector field, and that Killing vector field can be written as some combination of d by d theta and d by d phi. And that same combination that's a Killing vector field on the two-dimensional sphere is also a Killing vector field for the Schwarzschild geometry. So the Schwarzschild geometry is spherically symmetric. Meaning it admits sets of Killing vector fields that are combinations of d by d theta and d by d phi that represent rotations about any axis. Now the next thing to notice about this metric is that the metric components are independent of the coordinate t. And that tells us that d by dt is a Killing vector field. So this geometry has a time translation symmetry We also refer to this as a static spacetime. And the word static comes from the following consideration. If we look at a t equal constant slice of the spacetime, so in other words, I just look at the line element or the metric for setting t equal to constant, then dt is 0. This term goes away, and the line element for a t equal constant slice is just 1 minus 2m over r inverse dr squared plus r squared d theta squared plus sine squared theta d phi squared. So you can see that there's no t dependence here at all. So that means this three-dimensional space doesn't change from one value of the constant t to the next. So we refer to that as static spacetime. Now let's take a closer look at the three-dimensional geometry of one of these t equal constant slices. So let's examine this 3D geometry. First of all, we need to understand the meaning of this coordinate r. So let's set r equal to a constant. So dr squared is 0, and what we're left with is the line element for a two-dimensional sphere of radius little r. So that means we can view this three-dimensional geometry as a set of nested spheres. So there's one r equal constant value, there's another, and so forth. So each one of these spheres has r equal constant and metric, which is r squared times d theta squared plus sine squared theta d phi squared. And now let's compute the area of one of these spheres. So the area is square root of the metric times d2x, and the metric, notice, is diagonal with entries r squared and r squared sine squared theta. So the determinant of the metric is r to the fourth sine squared theta. The square root of that is just r squared sine theta. So our area is integral, and we'll integrate from 0 to pi, and theta and phi goes from 0 to 2 pi, times the square root of g is r squared sine theta. And the result of this calculation is, of course, the standard result for the area of a sphere, 4 pi r squared. So this is telling us that the coordinate r is related to the area of a sphere by the usual flat space relationship. On the other hand, let's take a look at the separation between two of these concentric spheres. So let's call this sphere R1 and this is R2. And let's look at this distance along a radial direction between R1 and R2. And what I mean by a radial direction is this is along theta equal constant phi equal constant. So in other words, it's along a constant angular direction. All right, if we set theta and phi equal to constants, then d theta is 0, d phi is 0, and ds squared is just 1 minus 2m over r inverse dr squared. So we have ds is equal to 1 over the square root of 1 minus 2m over r dr. And now we can integrate that to find the total distance from r1 to r2. So the total proper distance is r1 to r2, 1 over the square root of 1 minus 2m over r dr. And that is equal to r times square root of 1 minus 2m over r plus m times log of r minus m plus r times square root of 1 minus 2m over r. And that all would be evaluated between r1 and r2. All right, the result is not really that important. The main point is that this is not equal to r2 minus r1. So this coordinate r that labels these concentric spheres does not tell us the proper distance between the spheres. R is sometimes referred to as an areal radius because R does tell us the area of a sphere using the usual familiar flat space relationship. Area is 4 pi r squared. So R is called the areal radius. R is not the proper radial distance. The next observation I want to make about the Schwarzschild geometry, let me first write the metric again in Schwarzschild coordinates. This is minus 1 minus 2m over r dt squared plus 1 minus 2m over r inverse dr squared plus r squared d theta squared plus sine squared theta d phi squared. Notice now this factor, which I'll remind you, it appears here as well as here. This factor is really 2gm over c squared r. Now this coordinate r labels concentric spheres within the t equal constant static slices. So as r increases, we go to larger and larger area spheres, and of course this factor, this term, goes to 0 as r increases to infinity. So in that limit, the metric becomes just minus dt squared plus dr squared plus r squared d theta squared plus sine squared theta d phi squared. And this is just the metric for flat four-dimensional space-time, written in spherical coordinates. So in other words, I could just change this part of the metric from spherical coordinates to Cartesian coordinates, and this would be then the flat 4D spacetime in Minkowski coordinates. So if we change this to xyz, then this metric minus dt squared plus dx squared plus dy squared plus dz squared. This of course makes sense. It's just telling us that far away from the massive body, so here's the massive body in the middle, far away the gravitational field is weak, so the space-time looks flat. And in particular, if we have an observer out here near infinity, this is telling us that this t coordinate is coincides with the proper time measured on a clock by an observer at infinity. So the Schwarzschild coordinate t has the interpretation of proper time as measured by an observer in this region far away from the massive body where the gravitational field is weak, near r equal infinity. And likewise, this r coordinate measures proper distance between these spheres near infinity. Now that we have a little bit of familiarity with the Schwarzschild geometry, we can begin to work out some of the interesting consequences. For that purpose, we'll need to solve the geodesic equations in various circumstances. So let's look at the geodesic equations in the Schwarzschild geometry. All right, we start with the components of the metric, g mu nu. They're minus 1 minus 2m over r. That's the coefficient of dt squared. Coefficient of dr squared is 1 minus 2m over r inverse. Then the coefficients of d theta squared is r squared, and the coefficient of d phi squared is r squared sine squared theta. So from here we can invert this matrix, which we need for computing the Christoffel symbols. Gamma, mu, alpha, beta is 1/2 the inverse metric, g mu nu, times partial alpha, g beta nu, plus partial beta, g alpha nu, minus partial nu, g alpha beta. So we can compute all of these. And then the geodesic equations themselves are x mu double dot plus gamma mu alpha beta x dot alpha x dot beta equals 0. In these equations, the dot denotes differentiation with respect to proper time tau in the time-like case. It denotes differentiation with respect to an affine parameter lambda in the null case, and it denotes differentiation with respect to proper distance s in the space-like case. So let me write down the results of this calculation explicitly. So I've written them out neatly here because we'll need to use these geodesic equations several more times in the future lectures. So recall the x mu's for Schwarzschild coordinates. They are t, r, theta, and phi. So these four differential equations right here are the geodesic equations. And also remember that there's a normalization condition. The normalization condition says x dot mu g mu nu x dot nu equals plus or minus 1 or 0, depending on whether we're talking about the time-like, space-like, or null case. So that's just the inner product of x dot with itself, and for Schwarzschild, here it is written out explicitly for the three cases, time-like, null, and space-like. Now I'd like to address the following question. How do we know that m is the mass of the body? By m, what I mean is the parameter that appears in the Schwarzschild metric. How do we know that that parameter corresponds to the physical mass of the central body? This raises the more basic question, how do we determine the mass of the body? Well, we determine a body's mass by its influence on another body. Say, a test mass. For example, let's consider an observer at some large R value. So here's our body, and here's our observer very far away. Now the observer can release a satellite into a circular orbit. So here's the satellite, and here's the orbit of the satellite, circular orbit about this central body at some large radius r. Now this observer and the satellite, they're in a very far away in a region where the gravitational field is very weak. So in that region, Newtonian gravity should hold to a good degree of approximation. So Newtonian gravity holds approximately for r very large. And in particular, that means that Kepler's laws of planetary motion should hold. Kepler's third law should hold. Now I'll remind you, Kepler's third law relates the period of the satellite to the radius of the orbit and the mass. So the period squared is 4 pi squared times the radius cubed divided by the mass. And now the observer simply turns this relation around to write m as 4 pi squared times r cubed over p squared. So the observer uses this to define the mass. So the observer can measure the period of the satellite, and the observer can also measure the aerial radius. And by the way, I see I've switched from little r to big R. What I mean here is that this is all happening at some large r equal constant, which I'm now calling big R. All right, so the observer can measure the area of this sphere that he or she sits on, and from the area deduce what the r value is, the aerial radius. And then from the period and the radius, use this to deduce what the mass is of the central body. Now let's show that this m, this mass, is the parameter that appears in the Schwarzschild geometry. And to do that, we need to examine the world line of the satellite. Now, the satellite is going to follow a time-like geodesic. With coordinate r equal to a constant, big R. So let's look for a time-like geodesic with coordinate r equal to a constant, big R. And let's also assume that theta is a constant, pi over 2. So we're assuming that the satellite will stay in the equatorial plane. And that's a reasonable assumption, because if we start the satellite in the equatorial plane and we start it moving tangent to that plane, then by spherical symmetry, there's nothing to make it that would make it veer out of that plane. So here are the geodesic equations, and we're going to set r equal to a constant, big R, and theta equal to a constant, pi over 2. So with these assumptions, r dot and r double dot are 0. So this term vanishes, this term vanishes, this term vanishes. And also theta dot is 0, so this term vanishes. Theta double dot vanishes, theta dot is 0. And here we have an r dot, so that term goes away. Here we have a theta dot, so this term goes away. So we can see that this equation just simply becomes t double dot equals 0. This equation is simply phi double dot equals 0. And this term, by the way, this term, since theta is equal to pi over 2, cosine of pi over 2 is 0, so this term is 0. So this equation simply tells us 0 equals 0. It tells us nothing. And this equation is not trivial. it tells us that m times r minus 2m, and this is, since r is big R, let me just write this as big R, m times big R minus 2m over r cubed t dot squared, and then this term is 2m minus r times sine squared theta, but theta is pi over 2, so that's just 1, times phi dot squared equals 0. So that's this second of the geodesic equations. And for the normalization condition, we have r dot vanishes, so that term goes away, theta dot vanishes, and sine of theta is 1, so the normalization condition looks like minus 1 minus 2m over r t dot squared plus r squared sine of theta is 1 times phi dot squared equals, and we're dealing with a time-like geodesic, so it's minus 1. So our equations reduce to t double dot equals 0, phi double dot equals 0, and these two equations. Now these equations are actually not too difficult to solve, so I'll just write down the solution, and you can verify that phi of tau, proper time tau, is equal to tau divided by r, capital R, times the square root of r over m minus 3, and t of tau is equal to tau divided by the square root of 1 minus 3m over r. And of course, r of tau is just big R, and theta of tau is pi over 2. So this is the explicit solution for a time-like geodesic at a constant value of r and in the equatorial plane. But actually the information we need for our present purposes is all contained in this equation right here. If we write this out, we have m over r cubed times r minus 2m t dot squared, and bringing this term to the right-hand side, let me write 2m minus r as r minus 2m, so absorb that minus sign in that factor, times phi dot squared. Now you see these two terms cancel. So what we find is the square root of m over r cubed, taking the square root of both sides, times t dot is equal to phi dot. So phi dot divided by t dot, that's just d phi dt, is equal to square root of m over r cubed. And this, of course, can be written as d phi equals square root of m over r cubed times dt, and we can integrate this, integrate over a complete orbit, that's phi from 0 to 2 pi, and t from 0 to the period p. So this gives us 2 pi on the left-hand side is equal to square root of m over r cubed times p. We can solve that for p and square it to make it look nicer. This is p squared equals 4 pi squared times r cubed over m. That, once again, that's Kepler's third law of planetary motion. And the m that appears here is the m that appeared in the Schwarzschild metric. All right, so if our observer does the experiment with the satellite, measures the period of the satellite, and at a certain radius, capital R, the observer will see that this parameter m is the mass of the central body. And by the way, one subtle point here is, notice that I integrated t, that's the Schwarzschild coordinate t, from 0 to p, but since we're at a large radial distance, this coordinate t coincides to a high degree of approximation with proper time on the observer's clock. So this p is the period as measured by that observer near infinity. Now let's recall the discussion from an earlier lecture. In general relativity, the gravitational force is really a fictitious force. It's really an acceleration. So as we stand on Earth's surface, so here's the Earth, here you are, and here's the normal force of the Earth pushing up on your feet. We feel this upward force from the floor, and it's accelerating us radially outward at 9.8 meters per second squared. This is counterintuitive since we think my radial distance from the center of the Earth isn't changing, so how can it be that I'm accelerating? And the answer is, of course, curved space-time. So let's compute the acceleration for this person. This person or particle that sits at a constant aerial radius, so we'll call that constant capital R. That's the radius of the Earth, and also stays at a constant angular location. Now recall that the acceleration is defined as the four-velocity covariant derivative acting on the four-velocity, like this, u alpha, del alpha, u mu, and that this is equal to x double dot mu plus gamma mu alpha beta, x dot alpha, x dot beta. And this, of course, if we set this equal to 0, this is just the geodesic equation. So here are the geodesic equations, and I'm just going to cross out the equals 0 here. And this first equation is the t component of the acceleration. This is the r component, the theta component, and the phi component. Remember, we're setting r, theta, and phi equal to constants. So that means this term vanishes, this term, all of these terms vanish. So this first equation just says the t component of acceleration is equal to t coordinate double dot. The r component of acceleration is equal to m times, now little r is set equal to big R, r minus 2m over r cubed times t dot squared. And these two equations just tell us that the theta and phi components of acceleration are equal to 0. Now what about this normalization condition? Well, this is just the condition that the four velocity is properly normalized, so it holds whether the world line is a geodesic or not. And since we're talking about a time-like world line, we'll take the -1 on the right-hand side and now cross out r dot is 0, theta dot 0, phi dot 0, so all these terms vanish. And this equation reduces to -1 minus 2m over capital R t dot squared equals -1. This equation is easy to solve. It just tells us t dot is equal to 1 over the square root of 1 minus 2m over capital R. So the right-hand side is a constant. So if we integrate this, t as a function of proper time tau is tau divided by the square root of 1 minus 2m over r. And now our world line is given by giving the coordinates as the functions of proper time. So there's t of tau. R of tau is of course a constant, capital R. Theta of tau and phi of tau are just constants. So this is our world line. For the observer that's standing on the surface of the Earth. And from this we can, of course, compute the four velocity. U mu is just t dot, r dot, theta dot, phi dot are the components. So that's 1 over the square root of 1 minus 2m over r is the first component, and the other components are all zeros. So there's the properly normalized four velocity. And now the acceleration we find just from these equations here. So a of t, the t component, is t double dot, but t double dot vanishes. because this is linear in tau. And a theta and a phi also vanish. The only non-trivial component of acceleration is the radial component. So that's m r minus 2m over r cubed times t dot squared. T dot is, well, there it is right there. T dot is 1 over the square root of 1 minus 2m over r. And we square that. So we have m r minus 2m over r cubed times 1 over 1 minus 2m over r. Now if I take one of these factors of r in the denominator and multiply it by this factor in the denominator, you'll see it cancels this factor in parentheses here. So we're left with m over r squared. All right, so the acceleration vector has components at is 0, ar is m over capital R squared, a theta and a phi are both 0. So from here we can tell that the acceleration of this person standing on the surface of the Earth is not 0, but we do need to be careful about interpreting this result m over r squared, because ar is just the component of a vector, and remember we can always change the components of a vector by just changing coordinates. So let's compute the magnitude of the acceleration. So the magnitude of the acceleration is the square root of a mu, g mu nu, a nu, square root of the inner product of a with itself. Now the only non-zero component of a is the r component, so this is ar, grr, ar, and that simplifies to just pulling the ar out. ar times square root of grr. So this is m over r squared, and remember grr is 1 over 1 minus 2m over r, so this is 1 over the square root of 1 minus 2m over r. So that's the magnitude of the acceleration, and it's in the radial direction. Now we can evaluate this result numerically, but let's recall that in deriving it I've set c and capital G, Newton's constant, equal to 1. So let's restore the units to this result. We have the acceleration is equal to capital G m over r squared times 1 over the square root of 1 minus 2 g m over c squared r. So remember the units of g are length cubed over mass times time squared, and the units of c, of course, are length over time. So you can see here this factor has the units of length over time squared, the appropriate units for acceleration, and this factor is dimensionless. So we can now plug in the following numbers. Newton's constant is about 6.673 times 10 to the minus 11 in meters, seconds, and kilograms. The mass of the Earth is 5.972 times 10 to the 24th kilograms. The radius of the Earth is about 6.371 times 10 to the 6th meters. And the speed of light, of course, is 2.997 times 10 to the 8th meters per second. So if we plug these numbers in, first of all, we find this term is about 1.4 times 10 to the minus 9. So this term is very small. In fact, we can ignore it. 1 minus this is approximately 1. So our answer to a good degree of approximation for the magnitude of the acceleration is approximately gm over r squared. And plugging these numbers in, we find the expected result 9.8 meters per second squared. So a person standing on the surface of the Earth, or any object at rest on the surface of the Earth, is accelerating in the radial direction with an acceleration of 9.8 meters per second squared. Now there's one subtle issue I'd like to address. Recall that the Schwarzschild coordinate r is an areal radius, so it's defined such that the area of the spheres is 4 pi r squared. So this r that appears here is the areal radius of Earth. So what is this number that I wrote down here? I just looked up the radius of the Earth on the internet, and this is the number I found. So is this an areal radius, or is it the actual radial distance from the center of the Earth? Well, I think no one has ever actually stretched a tape measure from the center of the Earth to the surface to measure the actual radial distance. So this is probably closer to an areal radius than an actual radial distance. But having said that, it doesn't really matter because the difference between the areal radius and the proper radial distance is very small. Now, how do I know the difference is small? Well, consider the Schwarzschild metric. The proper radial distance, ds, is related to changes in areal radius by ds squared equals 1 minus 2m over r inverse dr squared. So in other words, ds is 1 over the square root of 1 minus 2gm over c squared r times dr. So now this term is the same term that we evaluated above. That was approximately 10 to the minus 9 near the surface of the Earth. So the difference between areal radius and proper radial distance is pretty negligible near the surface of the Earth. Now, what about inside the Earth? We don't actually know what the metric is inside the Earth, but one thing we do know is that the gravitational field is even weaker inside the Earth than it is near the surface of the Earth. So the difference between proper radial distance and areal radius should be even smaller than this 10 to the minus 9 correction here. So the conclusion is it doesn't really matter whether we consider this r to be an areal radius or a proper radial distance. The difference wouldn't affect this result in a significant way.